All right, college algebra students, we're going to be making a move to Chapter 5, and what we're essentially going to do is carry on a conversation that we've been having, but just very, very limited. So we're going to be focusing on polynomial functions. I think you guys kind of know what those are, but there will be some new definitions, some new theory, some new things to look at, but hopefully we can keep it grounded in the key ones that we know, and we'll see that story continue to unfold as we move through Chapter 5. But in 5.1, we're going to get a general overview of polynomial functions, and we'll start off with their definition. All right, it looks like a very complicated definition, but when we really look at it, it's not. So here's what it is, right? A function is a polynomial if it can be written in the form f of x equals some a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot 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 dot, a to the 1x plus a0. All right, and then n is any number between 0, 1, 2, 3, 4, and on and on and on. So it's basically a positive integer. So no negative integers allowed. And so what in the world's going on here? Well, all the little a0s, a1, a2, a3, all the way to an, these are basically what we call our coefficients. And because n can go to almost infinity, right, there's not enough letters in our alphabet, so we start using what's called indices. So the nth degree term has a sub n coefficient. We otherwise know that as the leading coefficient. All right, and we've seen how that does some pretty amazing things in terms of telling us whether our parabola is opening up or down, whether our line's increasing or decreasing. That's that role. And then all we're basically doing is, in terms of the degree, we're starting with an nth degree term, and then the next term would be n minus 1, and we're just going to keep going down until we have the constant term. And so that's essentially, that's what all these are. They're just basically coefficients, and we're basically looking at degree n polynomial. So an n degree polynomial. So mathematicians try to be as general as they can. And so let's go ahead and just start looking at some examples, and then we'll kind of fill in these roles, and you'll see that it's just a notation you're going to have to get used to, I suppose. So here's some examples. So we're going to define, right, whether these expressions down here are polynomials or not. Essentially, do they fit this definition? If they do, then it's a polynomial. If they don't, then it's not. All right, and so f of x equals 3. Well, this is what we called in the past a constant function. All right, and in terms of our terminology, there is no variable x. So we basically have n equal to 0, and it essentially means that a of 0 is equal to 3. And so that's using the new terminology here. If we were to graph this function, right, it's going to be a horizontal line at y equals to 3. And so this would also be a degree 0 polynomial. So since it fits my definitions, basically it's a to the 0, this is, technically speaking, a polynomial because it fits our definition. The next one we know to be a line. All right, it's a linear equation. But in terms of what we're doing here, we have n is equal to 1. And our a sub 0 is negative 2. And our a sub 1 is 3/4. Of course, we knew these as m and b back in our day, right? Y equals mx plus b. So we're just changing, coefficient basically. We're just changing their names, and so we can handle an nth degree polynomial, not just a 0 degree or degree 1. But since n is equal to 1, we're just basically using an indice to write as big or as small as a polynomials that we want. So hopefully that terminology, again, we're just shifting gears. Rather than calling things m and b, we're calling them a1 and a0 respectively for degree 1 polynomial. So this, again, is a polynomial because it fits, all right, our definition, at least for n equals to 1. Here's another one. We know this to be degree 2, and we also know it's a quadratic. And in this case, n is equal to 2, and our a sub 0 is negative 3, our a sub 1 is negative 1, and our a sub 2 is positive 2. So the leading coefficient the next coefficient, and the next coefficient. N is 2, N is 1, N is 0. So we're just going downhill from there. And so we can define some pretty big polynomials as we go along. For example, f of x, let me just do one more, equals 3x to the 7th plus 2x to the 6th plus, let's say, x to the 5th minus 2x to the 4th plus 3x cubed minus 7x squared, hope I'm running out of room, minus 8x, and then plus 10. Sorry, I ran out of room there. So we basically have a degree 7 polynomial here. Right? That's a pretty big one. So n equals 7. So that means a sub 0 is the constant, that's 10. A sub 1 is the first degree term, so that's negative 8. A sub 2 is the coefficient of the second degree term, so that's negative 7. A sub 3 is the coefficient of the degree 3 term, so it's 3. A sub 4 is negative 2. A sub 5 is 1. A sub 6 is 2. And a sub 7 is 3. So these are just ways that we designate the coefficient for each one, and this is basically a polynomial. Some things that are not polynomial, if we look at this next one, right here, this is good, right? That's x to the first power, but technically speaking, that's x to the 1/2 power. Our n's have to be nice, perfect, positive integers. So that guy ruins it for everybody. This is not a polynomial because it doesn't fit the definition of a polynomial. Same thing here, it's ruined by both, right? Here n is equal to negative 2, here n equals negative 1. I want my n to be positive integers. So again, this is not polynomial because it doesn't fit our definition. We can't write it in terms of terms with n being a positive integer. Here we're doing a division. So before, keep in mind we're talking about the word can be, all right? And so can we rewrite this so that it fits my polynomial definition? So if we just do the division, this is x cubed over x squared plus 2x squared over x squared minus 3x over x squared. Do some simplification, we get x plus 2, and then this would be minus 3 over x. Or in essence, this is x plus 2 minus 3 to the x negative 1. So that guy's okay, that one's okay, but that one's not, because we have an n equal to negative 1, and that does not fit our definition up there. So this, at the end of the day, is not a polynomial. All right, trying to get a little harder. The next round, what I'm doing actually here is I'm actually multiplying. But if we distribute, we get 2x squared minus 3x. And that basically fits our definition for a polynomial. We're degree 2, so n is equal to 2. There is no constant, so a0 is 0, a1 is negative 3, and a2 is the leading coefficient. So this is a polynomial because it does fit the definition that we're trying to fit. All right, a little more complicated here. We have things that are nice and factored. But if we would actually expand this out, which I'm not going to do at this moment, but we can eventually rewrite it, right? Because this, the first term right here is 1/2 x minus 1/2, and this is x plus 4 times x plus 4. And so if we just did one round, or how would I do a couple? This is x squared, I think 8x, yeah, 8x plus 16. And then if I would do another round, we would have 1/2 x cubed, right? It looks like plus 4x squared, and then plus 8x. And if I did another round, might as well just keep going. Right, this would be minus 1/2 x squared minus 4x, and it looks like minus 8. All right, and if we combine like terms, we have 1/2 x cubed. There's an x squared, I think that's 3.5. Which is 7/2 x squared. We have an 8x and a minus 4x, that's positive 4x, and then a minus 8. So after expanding this out, we can actually write it in terms of the definition form. Here n is equal to 3. And so our a sub 0 is the constant, negative 8. A sub 1 is 4. a sub 2 is 7/2, and a sub 3 is 1/2. So that, even though it's in factored form, it can eventually be written as a term decreasing in order, right? As a matter of fact, I think this we call that descending order. So this ultimately, I think I lost my, is a polynomial. And then last but not least, if we do the division like we did on this one, we get x cubed over x plus 2x squared over x minus 3 over x. Doing some simplifications, we end up with that. And that is definitely a polynomial of degree 2. All right, it fits our definition. So a0 is -3, a1 is 2, and a2 is 1. So that is our official definition of a polynomial. All right, we either have the polynomial straight out, we can prove that it's not a polynomial. It's usually something regarding with n. It's either a fraction or a negative, and that kind of throws a curveball at us. Or if it's in factored form or some division form, if we do some simplification, it can be actually written as a polynomial in descending order. All right, so there's your definition, and we're obviously going to build more onto this and do more things. See you guys in the next video.